All right. It's going to be the last section for this week. Going to take a look at some circle theorems where we actually get to use all of that quadratic formula business that we spent so many minutes practicing. So let's take a look at those theorems. So 10.6 is finding segment lengths in circles. And the first one is all three of these theorems actually have pretty cool names versus like 10.7 and 10.8 and that business. So the first theorem is segments of chords. When you have two chords that intersect inside a circle like this, if you take the product of the two sections of one chord, that equals the product of the two sections of the others. So if I took a look at B, E times BC, the product of those two guys is exactly equal to the product of the two other sections. In the next theorem, the segments of secants, this one here, when you have two secants that intersect outside the circle, the product of the section that's outside times the entire secant, those two products are going to be equal. So AE times EC, which is the entire secant, that's going to be exactly equal to this outer portion times this entire secant. And the third theorem is actually pretty much the last theorem we just looked at, only if one of the segments is a tangent. Here, the tangent squared is exactly equal to the product of the exterior part of the secant times the whole secant. So ED is the entire secant, EC is just the exterior part. So the tangent squared is equal to the section of the secant that's outside the circle times the entire secant. So three theorems, they all say very, very similar things, and they're all multiplying portions of line segments. But we are going to see much more interesting and colorful problems here. Speaking of that, I'll try and color code this a little bit. So in this first situation, we have the two chords. That's not focused. That's not focused either. All right, that's okay, I guess. We have the two chords intersecting inside the circle. So the product of this portion times that portion is going to be exactly equal to this portion times that portion. Now, here's where foiling and the quadratic formula come in. I'm going to goof that up a little bit. So here we'll just distribute x squared plus 4x. And on this side, we're going to have to FOIL that out. So x times x is x squared. X times 2, 2x. 1 times x is x. And then 1 times 2 is 2. And what did I miss? This, okay. So let's clean this up a little. X squared plus 4x equals x squared plus 3x plus 2. Now this one's very convenient. We don't actually need the quadratic formula here because the x squareds subtract right out of both sides, and now we just have 4x equals 3x plus 2. Subtract the 3x from both sides, x equals 2. So now we know x equals 2. Let's figure out all these other segments here. AE is just x, so that's 2 units. BE is x plus 2, so that's 2 plus 2, 4 units. CE is x plus 1, so that's going to be 3 units. And then DE is x plus 4, so 2 plus 4, 6. And let's just sort of double check our little situation. Excuse the bad drawing there. So we had 2, 6, 3, and 4. Oops. 3 and 4. And it shows that the product of these two, 12, does in fact equal the product of those two, 12. So it's a nice little check there. All right, on to situations where we may end up with the quadratic formula. Now, in both these next two situations, it involves multiplying, well, at least in half of this situation, and both times in this situation, multiplying the part on the outside by the entire secant. So the entire secant here, we'd add these two together. X plus 2 plus 3 is actually x plus 5. And similarly here below, we have this secant AE. We would add these two together. So x plus 1 plus x minus 1. Well, x plus x is 2x. And then plus 1 minus 1 cancel each other out. So just a little off to the side action, you are going to need to add some things together to get the entire secant. Okay, and now the theorem says if we multiply the portion on the outside times the entire secant, those two products are equal. So the portion outside times the entire. Okay, we're going to have some distribution to do here and some simplifying, and maybe we'll get lucky and have to use the quadratic formula. Won't that be fun? So distribute 3x plus 15, distribute 2x squared. 2x times x is 2x squared plus 2x. And I do have an x squared and an x and a constant. So we have an a, a b, and a c. Let's move everything to one side of the equal sign and just the plain old 0 on the other side. So I have a 2x squared minus x minus 15 equals 0. And now, of course, we have our most excellent quadratic formula. And our a value is 2, our b value is -1, and our c value is -15. Let's use the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac all over 2a. simplify. So negative times negative is positive. Negative 1 squared is 1. Negative 4 times 2 is negative 8 times negative 15 is positive 120. And that is very convenient because 120 plus 121 is a perfect square, 11, so we get 1 plus 11 over 4 and 1 minus 11 over 4. Now 1 plus 11, 12 over 4 is 3, but 1 minus 11 is negative 10 over 4 is negative 5 halves. Now hold up here a second. Looking back at the original problem, algebraically both of these are values of x that make this equation true. However, take a look at this x minus 1 here. We got an x value of negative 2.5. Negative 2.5 minus 1 is negative 3.5. This distance is not negative, it is positive. So even though algebraically we get two answers, one of them doesn't actually make sense because we get a negative length there. So 3 is the only one that makes sense. That gives me a 4, a 2, and a 5. So the only value that we're going to use for this problem is the value of 3. That's going to make a BC equal to 5 meters. AD is going to equal 4 meters. And DE is going to equal 2 meters. Just like I did in the last problem, just a quick little check to show that the theorem is working. Ooh, this is not drawing a scale at all. So we got a 3, a 2, a 5, and 4. This whole thing is 8, and this whole thing is 6. And I labeled the problem wrong. I goofed this up. This is a 4, and that's a 2. And that's why the numbers weren't working out. Plus, silly me. And that one's a minus. I just switched those two in my mind. Bad call. All right, so the product of the portion outside times the whole thing, so 4 times 6 is 24, equals the product of the portion outside times the whole thing, 3 times 8, 24. All right. So one last problem here. This time we've got an entire tangent that squared is going to equal the product of the portion on the outside times the entire secant. We are going to need to distribute there. So 16 times 16, I believe that's 256, equals x squared plus 8x. I'm going to subtract 256 from both sides, so we can get a 0 on one side of the equal sign. Quadratic formula now. A equals 1, B equals 8, C equals negative 256, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. All right, let's clean this up a little bit here. So negative 8 plus or minus 8 squared is 64. Minus times a minus is a plus. And 4 times 256, it's 1024. All over 2. It's 1088. I'll double check in a second. I gotta pick my calculator up. I suspect, by the nature of these problems, that 108 it's not a whole number, but it divides out of 64. And then we can divide the whole number 2 out. Now x is a length, so negative 4 minus 4 root 17 is not a positive value, but negative 4 plus 4 root 17, that is a positive number. So our actual answer is actually only negative 4 plus 4 root 17. All right. So it got difficult quick, especially with this new algebra. That's why I only did 2 circle sections this week and 1 we just practice algebra section. Setting the theorems up aren't super complicated, but then it leads to some tricky algebra, so be careful about that, and definitely give us an email if you have questions.